4, 5, 6, 7, 8. Okay, not a lot. Oh, there's the sound of a Rubik's Cube. Wait, I'll put it away once I'm done. Should I be expecting anyone else? I guess I'll start at 8 exactly lah. It's a bad idea to have this at night. But because of my current internship, we don't have a choice. Once we hit 29th May, afterwards we can have this during the day lah. Okay, it's 8 o'clock. What to start with? So basically, I will be covering E&M. I'll be covering electromagnetism with you guys. And okay, before I start, okay, I did this with my previous class as well. I want to moderate your expectations a little bit first. So this is going to be a physics class. It is not going to be a physics Olympiad class. And what this means is that I'm not going to be super focused on all of your Olympiad questions. And some of the material that I cover, right, is not going to be tested in the actual papers. So the reason is because the physics Olympiad really just takes a small section of a lot of different things and jumbles them together. So it's not a very coherent way of learning if you just learn based on the physics Olympiad syllabus lah. So if you guys want to do well in the Olympiads, that's fine. My advice is just go online and look for a lot of different exam papers and just do those questions and you'll be fine. Silver or gold should be no problem. But the goal of my lessons is not so that you will do well in a competition per se, but so that you have a little bit more understanding of EM as a topic. Okay, so far so good. Oh man, it sucks to not have a response. So the bulk of EM is basically, there's only one question that EM is trying to answer. And the question is this: if I have a collection of charges, right, how will the charges move? And this seems like a very simple question to ask. Like we all know that if you have a positive charge, if you have a positive charge here and you have a negative charge here, you're going to expect them to attract. If you have a positive charge, you have a positive charge, you're going to expect them to repel. But on paper, even though this is an easy question, right, it is mathematically extremely complicated. And this is because what we know as the attraction between a positive and negative charge is just one of three different levels of abstraction you can go into when you talk about electromagnetism. Oh dear. And in general, there are three things at play. The first is electrostatics, which is simply just your Coulomb's law. Beyond that, we have magnetism. And what this means is that once your charges start to move, right, they'll start to produce a magnetic field, and the magnetic field will influence the other charges around them. And the third thing that comes into play is relativity. And relativity basically means that your electric field and your magnetic field produced by your charge cannot change instantaneously. Because the information can only travel at the speed of light, right, you're going to expect some delay. And these three basically cover the entire bulk of electromagnetism. when it comes to your Olympiad level, right, you actually only really need to know the first two. And I'll be spending most of my time covering the first two, and I'll move to the relativistic part only if time permits. Okay, so let's start with electrostatics. And electrostatics is really very simple. It's basically just one very simple statement, which is Coulomb's law, which states that F is equal to so it's written in the worksheet over there for you. So it is inversely proportional to the distance between two charges. Is my handwriting too small? Can I zoom in? Okay, so it's inversely proportional to the square of the distance, and it is directly proportional to the two separate charges. Okay, and in all of my worksheets, you're going to see this notation, this RQQ notation. And this is just because, right, my LaTeX doesn't have the font for this is what you will typically see in Griffith's book, which is the vector of separation. Actually, maybe let's talk a bit about before I get into the content. Let's talk a little bit about the materials that are available to study EM with first. And I think the general three books that people will recommend will be the Purcell and Morin, the Griffiths, and the Jacksons. And Purcell and Morin is basically the most simple of them, and it is the most level appropriate. So if I were to recommend you to study anything, you should study Purcell and Morin. Yeah. Griffiths is slightly more complicated, and I would say it is a little bit above the level that you currently need to know. But I'm going through Griffiths because I have the physical copy of the book, so it's convenient for me to refer. And Jackson is a graduate level textbook, which means that it is extremely, extremely tough. So if you want to do Jackson, you have been warned, it is not easy. Okay, and for any of you who are thinking of buying Griffiths or torrenting Griffiths, I just need to know that the Griffiths is a little bit light on the mathematics. Basically, the math that is presented in Griffiths is not particularly rigorous. So when you do the problems, keep in mind that you know a lot of the proof is left out for the sake of being understandable. Okay, so back to this. So, am I going too fast? Can I be understood? Oh, okay. Yeah. So basically, electrostatics is just about Coulomb's law. And Coulomb's law is also a very, very simple law. It's a okay. How should I go about doing this? Okay, let me explain my notation first. Okay, so whenever you see any Q's and any Q's, right, just keep in mind that if you see a capital Q, this represents a test source. And when you see a small q, this is the source charge. So when you see something that says RQQ, this really just means it is RQ minus RQ. And RQ minus RQ, if you think about it, so if this is Q and this is Q, this is RQ, this is RQ. RQ minus RQ will be this vector. So this is RQQ. It is the vector that points from small q to big Q. And yeah, all of you know Coulomb's law, so I won't elaborate. But if you see the Google Drive, you know that there are going to be 7 worksheets on Coulomb's law. And the bulk of these worksheets is really talking about what this specific 1 over r squared relation means, or what properties of this 1 over r squared, or what can we extract from this one simple equation. Okay, so I guess for right now, just try problems 1.2.1. It's a very, very simple problem. I think you guys will not need more than 3 minutes to do it. So up until 8:11. Okay, so problem 1.2.1, no problem, right? It is the only, I mean, it is the easiest problem in this entire sheet. And you'll probably never ever get to see a problem as simple as 1.2.1 for the rest of the worksheets. So learn to appreciate it. So anyone who's done the question want to explain your answer? Anyone? Okay, I'm just going to pick a random name because I trust all of you can do this. And for the one person who decided to come into an EM lecture with the name Laplace, right? Yeah, you're it. Can you unmute your mic and explain your solution?
Oh, hello. So, for the 12 equal charges, we just because by the superposition principle, we can just sum up all the different forces on all the 12 charges. So we multiply each force multiplied by 12, and then we know the. Oh wait, what am I saying? The force is 0. Yeah, sorry.
Yes, the force is 0. Why is the force 0?
Because it's at the center, and all the charges are at the corners.
Okay, so that's right. If you were to take a look, right, okay, I'm not going to bother drawing out all 12, but if you have a charge here and you have a charge here, it is symmetric about the center, so the force of this on this is going to cancel with the force with this on this perfectly. So this will happen for all 6 pairs. So you expect the force to be 0. What about part B?
So if you remove one charge, then there will be a net force on the thing. If all are still at the all of them are still at the 12 corners. So
Okay.
now there will be a net force.
Okay, so the force will be 1 over 4 pi epsilon 0 q over r squared in the direction of the charge that you remove.
Yeah.
Okay. Then what about part C? Now there are 13 charges, so it's an odd number.
Where's the 13th charge, please? Or just any random
It is
position?
still a regular polygon, so it is still evenly distributed.
Okay. The force will still be 0.
Why will the force still be 0?
Because it's still like 13 sides.
Okay. That is a somewhat unconvincing argument. Can you do any better?
Because the net force will still all of them are still all of them are still.
Okay, I think we have lost you. Okay.
Actually,
so the answer is very trivial. We all know that if it is 13, the net force is going to be 0. But the question comes in how you explain why it is 0.
because if we take a look at a 13 sided polygon, then we can see that each charge opposite it. So there will be 2 charges right next to the. If we just examine, there will be charges. The charges opposite will still cancel out.
Okay.
By.
Let me end your explanation, because you're right. It is going to be 0, and I know you're struggling to come up with an answer why. But you're not going to go anywhere with a this charge cancels that charge kind of argument, because 13 is a prime number. And the best way to see why this is going to be 13 is that let's just look at the center charge, right? And if we look at how the forces look like going around this charge, it is going to go in a circle with a regular angle over here. So what happens if you join all of these head to tail, right, is that you're going to form a 13-sided regular polygon. Okay, and 13 sides is a lot to draw. So it is going to point like this, and if you trace all of these up head to tail, you're going to end up right back where you started. Okay, is that clear? Yeah. So this is the reason why f is going to be equal to 0. And you're not off the hook yet. There's still part D. Are you still there?
Oh yeah, hi.
What will your answer for part D be?
One of the 13.
One of them has been removed.
So it sounds like a trick question for some reason.
Okay, intuitively, what is your answer going to be?
Is it 0? Is it still 0?
Why would it still be 0? It is not 0.
Or it's probably going to be I feel it's going to be the same as the
Same as
one
B,
of the
right?
12, yeah.
Okay. The reason why it's same as B is also very simple. And there are actually two ways to do this. The first way is the not so stupid, is the not so clever way, which is, okay, we're going to go back to the idea that these 13 forces is going to form a 13-sided regular polygon. So what happens if I were to say remove one of these? If I were to remove one of these, right, I can still start from here and trace the entire polygon. But when I'm done, right, I'll end up with a resultant force that looks like this, right? So what this means is that we're going to expect an attractive force in the point where the charge has been removed. And this is going to have magnitude 1 over 4 pi epsilon 0 QQ over R square. But the slightly cleverer way to do this, right, is to take note that they are charges. So you can always just apply principle of superposition. And what you can do, right, is that with your 13 charges, right, we know that if there are 13 charges, that at the center, the force is going to be 0. So if you want to imagine what happens if you take out a charge, it's the same as simply just adding a negative Q over here. Is it a negative to begin with? No. Yes. So basically, if all of the charges are present, there's no force. Oh my goodness. And if you were to impose a negative Q, you're going to get a situation where there are only 12 charges. Then what it means is that basically your situation with all 12 charges plus the force contribution by this minus Q is just going to be your answer, which is just going to give you a force that points in this direction with magnitude of this law. Is that clear? Okay, I felt like that was not clear at all, but never mind. I will not dwell on this question for much longer. The basic principle is that, yeah, you can use superposition. And for those of you who, oh, I haven't introduced the principle of superposition. Okay. No, but you guys know what the principle of superposition is, right? It just means that if you have two charges and you add a third charge, the force between the two charges will not change. So basically, yeah, if I have a test charge here Q, and I have say Q1, Q2, Q3, and whatever nonsense, the force on Q is just going to be the vector sum of this plus this plus this. Okay, there is no funny nonsense that prevents you from adding this up like usual vectors. Okay. In any case, this is a fully written out answer. Is it? This is a fully written out answer. If you guys want to take a look at how you would present it in a competition. So, my goodness. Okay, the reason why my phone is spazzing out is because I'm holding it down with a book. Give me a moment now. Okay, all clear? Blah. Okay, so let's move on. And the next part that I'm going to talk about is I'm going to talk about what the electric field is. So basically, if you have a bunch of source charges again, and again, we always represent source charges with a small letter q. And we bring in some test charge here q. What we do know, right, is that the force on this test charge q is going to be directly proportional to q. It is always going to be directly proportional to q. And because of this, right, we can simply just take away this q, and we can call this the constant of proportion, or we can call this proportionality constant just the electric field. So basically, instead of depending on a test charge to define the system, we can just express it as a force per unit charge everywhere kind of thing. And what this does is that it's basically the electric field at any point, right, would be just be given by this. So what you notice is that your big Q is missing from the top, your big Q is missing from the top. And this is where things are going to get a little bit confusing, because there is still a big Q here in the subscript. And what I want you guys to remember is that whenever you see a big Q, you're just talking about a position where a test charge is supposed to be. So there doesn't need to be a physical, oh my goodness, there doesn't need to be a physical charge for there to be a big Q. Yeah, so the relation between force and electric field is just going to be F is equal to Q times E. Okay, so 1.3.1 and 1.3.2 are, again, very straightforward questions. I want you guys to give it a go now. I think it's slightly more challenging than the previous one, so I'll give you 5 minutes. And for those of you who are done, just WhatsApp me the solution now. Okay, and if I'm going too fast, please tell me. Okay, so the starting is going to be a little bit slow because yeah, if I go too fast at the start, I think people are not going to want to come for future lessons. So let's take things easy and just do simple E field calculations. Why is there an E naught in your answer? What is E naught? Oh, epsilon zero. Okay. Nope, it does not look to be correct. Sorry, not correct. I think you forgot to resolve the direction of your forces, of your electric field. Ah, my goodness. Oh, you're presenting the limit, is it? Ah, the limit is correct. Yeah, this is the correct limit. Did the question not ask you for the... No? Oh, the question is asked what is your limit in the limit. Correct. Yeah, your limit is fine. Just need to put in a z hat, then you should be fine. Hmm. Can you answer for 1.3.2? Still doing? Hmm. The limit is not zero. It is close to zero, but you can always get higher order terms. Okay, zero is actually quite a funny answer. But yeah, it's not zero. I don't know. Anyone close to the answer? Okay, anyone close to the answer? If you're not close to the answer, please type no. Oh, okay. Oh, so that's how it's done. Okay, I'll give you guys 3 more minutes. If nobody sends me the answer, I'm just gonna go throughout. So 8:37. Okay, so it is 37 and nobody has sent me an answer for 1.3.1 and 1.3.2. I'm just going to assume that all of you have attempted the problem. Okay, so we do have a answer for the first part, right? The 1.3.1. So whoever sent me the answer, can you just unmute yourself and explain? Yeah, this guy. 88282134. Do me a favor, unmute yourself and explain 1.3.1.
Hear me? Hello.
Hello, hello. Hello, hello. You're a little bit soft.
Okay, I'm not sure who. Hello. Okay, so in is just adding the vectors.
Okay. So what did you get for the electric field before you took the limit?
I didn't bother.
You didn't bother. That's fine. That is a perfectly fine way to approach this question as well. The question didn't ask you to explicitly solve for the electric field, right? Oh no, it did say find the electric field. Okay. Never mind. Let me just go through the answer for both of these parts. So before we actually try to do solve for the electric field, let's just take a look at what these two or what the physical situation looks like. Yeah, that looks to be correct. That looks to be correct. Okay, so in the first scenario, you have two positive charges here, QQ. So what it's going to produce is two electric fields that look symmetric. That looks symmetric like this lah. And this is going to give you a net electric field in the z direction. A net electric field in the z direction. In the second case, so you have Q, you have minus Q. In this particular case, let's just call this Z and call this X now. In this particular case, the force in the Z direction gets cancelled out, and you're going to end up with a net force in the X direction. And intuitively, right, we are going to expect that this force is not going to be quite as big as this force. Is that clear? So let's answer the question of what is the limit when you go very far away? Well, when you go very far away from a system with 2Q, right, what happens is that this distance over here, right, is going to look smaller and smaller and smaller. And eventually, this is just going to look like a single point charge with 2Q. So this is why in the limit, where you're very, very far away, right, you're going to expect this to be 1 over 4 pi. Oh my goodness. You're going to expect this to be, let me use the darker color. 1 over 4 pi epsilon 0, 2Q over z squared. Is this clear? Again, I repeat, when you're very, very far away, right, what you're going to see, right, is that these two Qs are going to act like a single Q. So it is going to look like this. In this particular case, right, you can make the same argument. You can say, oh, when you're very, very far away, right, it's going to look like a Q and a minus Q put together. But what is that? That is just 0. So yes, when you're very far away from this system of charges, right, it does in fact look like 0. But it is not exactly 0. It is just close to 0. And what we're interested in is how fast this electric field is expected to fall away. Okay, and this is something that we call the multipole expansion. And this particular Q minus Q is going to be something that you're going to see a lot. This is what we call a dipole. Okay, and we're going to in fact have two worksheets talking just about this Q and minus Q system lah. But it is a slightly advanced topic. As of right now, we're just interested in the most basic, which is the electric field. So let us start with the simpler case first. With this case, what you want to do is that, let me turn to a fresh page. Or in fact, let me just present my already written answer. The first thing that you're going to do is you're going to want to perform some geometry, because we know that there is a 1 over r squared relation, but the r that we're talking about is this diagonal distance. So in order to get this diagonal distance, we're going to have to use a little bit of Ko-Kuting-Li. 0 times L over root Z squared plus L squared. Okay, we'll go through it in a bit now. So we have, oh my goodness. Okay. We have the 2 over here is your contribution from 2 separate charges. Your 1 over 4 pi epsilon 0. Then your Q over R squared. And the final term here, right, is to resolve it in the Z direction. Because we know that by symmetry, anything in the X direction has been cancelled out. So you will do the math and you'll eventually get this, okay? And remember that E is a vector. So you always want to put a, like basically you can't leave this in scalar form. You can either write it like this or you can write blah, 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 pointing in the Z direction. So in the limit where Z becomes much greater than or equal to D, right? Well, what you can do with the bottom, right, is, okay. What you can do to the bottom right is that you can take your Z out from there and you get a 1 plus D over 4Z squared over here, right? And what we do know is that because Z is much greater than or equal to D, this thing we're going to expect is going to be very, very small. Since it's going to be very, very small, we can just Maclaurin this bottom part. And what we do get is that, you know, all the higher order terms can be thrown away. And this does eventually lead us with this correct answer, which is indeed the charge produced by 2Q at the origin. Okay, so this makes sense. This is an intuitive answer. In the second part, the only thing that has changed in your expression here, right? The only thing that has changed in your expression here is this term. This term has changed because, well, you're resolving it in a different direction now. So you can do the math, and you end up with an expression like this. And same thing, when Z is much larger than D, you can take the Z out from the bottom and you can do a Maclaurin expansion here. And what you do get is that it is going to fall off as Z cubed. So from very, very far away, right, we're going to expect a dipole's electric field to fall off with slightly faster than we do a single monopole. So this Z cube relation is quite an important relation. So it will be good for you to take note. Okay, so far so good. Am I going too fast? Okay, no answer means no. The next part of the worksheet, right, we're going to be talking about continuous charge distributions. And continuous charge distributions is basically the same as if it's just regular, except you have to do some integration. And before we start with any of the integration, let's just go through some common notation. So if you have a line charge, we typically use lambda to denote the charge per unit length. So the charge by segment dl is going to be lambda dl. So we have dq equal to lambda dl. For a surface charge, the typical symbol that we use for surface charge is sigma. And when we talk about a small surface element, we always call this dA. So we have dq equal to sigma dA. Then if you have a volume charge, we're going to expect, we're going to call the volume charge distribution rho, and we are going to call this particular small segment dV. So dq is going to be equal to rho dV. Okay, so these are just standard notations that you will sometimes see in questions. Sometimes they will just show you sigma equals to something, and they will not tell you what sigma is. So just keep in mind that when we say sigma, it's always a surface charge. When we say rho, it is always a volume charge. And lambda is always a line charge. Okay, and now here are, okay, so basically problems 1.3.3 to 1.3.10 should really just be renamed practice for integration. So it is just a bunch of integration questions. So I won't dwell on it too much, but I'm going to go through basically 3 different substitutions that we commonly see. Okay, 3 different substitutions that we commonly see in all of these problems. And basically, in most H2 problems, if you have a integration by substitution question, right, you will normally be given a substitution. But if you see these questions in the wild, right, they typically don't give you the substitution. So what I want to tell you now is how you can figure out what is an appropriate substitution. And basically, the way to figure out what is an appropriate substitution is you should really just look at what is the range and what is the domain of x, or basically, what can x take? So for instance, right, if you have a square root 1 plus x squared, well, a square root 1 plus x squared term, 1 plus x squared is defined everywhere. So this is going to be a real number for any possible value of x. So it makes no sense to say substitute x is equal to cosine theta. Because if you substitute x is equal to cosine theta, you're artificially limiting x to say, oh, this is between -1 and 1. And similarly, it makes absolutely no sense to say, okay, I'm going to substitute x is equal to secant theta. Because again, unless you know for sure that x is going to range from 1 to infinity, if you do this, right, and x is a negative number, then this substitution is obviously not going to work. So whenever you see something that looks like 1 plus x squared, you need to think that you are going to think of a function of x, right, that can have, basically, this function can have values of x everywhere. And the most commonly seen functions we have are tangent theta and sin h of theta. Sin h of theta. Yeah, so tangent and theta, sin h of theta, these are appropriate substitutions if you see a square root 1 plus x squared. If you see a square root 1 minus x squared, well, this is only defined for x between -1 and 1. And because it is only defined for x between -1 and 1, right, the most commonsensical things to try is just, okay, this is going to be cosine or sine. And likewise, if you see an x squared minus 1, this is going to be valid for, oh Jesus Christ, this is going to be valid for x more than or equal to 1. Okay, so in this case, what you're going to think about is I can sub in a cos or I can sub in a secant. Okay. So far so good. So these are your math tips. There is one particular question that I am interested in going through, which is the one on the sphere, the spherical shell, which is problems 1.3.8. Okay, and problems 1.3.8, if you know Gauss theorem, it is very simple for you to do. You can just apply Gauss theorem here and poof, the answer comes up. But the point of this question is not to use Gauss theorem, is to make you work for Gauss theorem a little bit, Gauss law. Yeah, to work for it a little bit and to understand why it is such an elegant and interesting theorem. I'll give you guys, okay, is this question doable in 10 minutes? Chris, do you think the question is doable in 10 minutes? Probably not,
Wait,
right?
which question?
1.3.8, the shell.
I don't think so.
Not doable in 10 minutes.
10 minutes, yeah.
Okay, I don't want to go through the question because the answer is very interesting. And oh, you guys have done this question under gravitation before already, is it? Okay. So okay, let me just cheat a bit. I typically don't like to do this. I typically like to give you guys time to try the problem. But this problem is just math, so there is no physical insight to be gained from doing the math. So I'm just going to walk you through, oh my goodness, the solution. Okay, I'm just going to walk you through the solution. Okay, so this is what our setup looks like. And what we're going to do, right, is we're going to be integrating across the ring. So basically, what we're going to do, right, is we're going to cut out this sphere into rings and integrate over each of these rings. Okay, and well, the first question that you want to ask yourself is, what is the charge contained within each ring? And the answer is, okay, let's just call this angle theta. Is, well, we expect the radius of this ring, right? We expect the radius of this ring to be r sine theta. Is that correct? Yes, that's correct. And we are going to expect this ring to have some width. Okay, let's just call this bigger. R d theta. Okay, we're going to expect this ring to have some width r d theta. So this particular ring, right, is going to carry charge sigma r d theta r sine theta. Is that clear? Okay. So if that is clear, basically what we're doing is we're doing just that. So is it the r times, oh, there is 2 pi r sine theta, yeah, because it is a circumference, so you're going to expect the 2 pi r. So 1 over 4 pi epsilon 0. The term on top here is, let me zoom in a little. Oh my goodness. Okay. Okay, so let's just focus on the integration. So the 1 over 4 pi epsilon 0 is always going to be there. Over here, this sigma r d theta 2 pi r sin theta, this is your dq term. And the bottom over here, right, is your r square term, which is basically, you can find this using cosine rule. Then the last term over here, right, the last term over here, it is basically you're trying to resolve this in the z direction. Okay, and after that, yada yada yada, do some math, and you get your final answer. Okay. It uses some opposite side of the sphere kind of argument, right? Most likely. Potential over test mass. Yeah, okay, doesn't matter. So at this point, we're going to realize an interesting fact. And the interesting fact, right, is that after you do the integration, there is a square root. There is a square root in the denominator. And why this is interesting, right, is because this must return you a positive value. And because this must return you a positive value, right, depending on the sizes of r and z, this can either be, after you take the square root, either be plus what is inside or minus what is inside. And this gives us two very distinct regions in which okay, two very distinct regions in which oh my goodness, Jesus Christ. Okay, basically, if your point is inside the sphere, you're going to expect the electric field to be equal to 0. And if your point is outside the sphere, you're going to expect that the electric field is going to look as though all of the charge is concentrated right at the center. Okay, yeah, there are many ways to prove this particular problem without having to use integration. That is true. And the reason why this is true for this particular problem is because you're dealing with a sphere. And spheres always have a lot of very nice symmetries that you can abuse. But when you are given a random charge distribution, if you're given something that is not so symmetrical as a sphere, right, you are going to have to end up doing the integration. So it is a good skill for you to learn. Okay? Yeah. But basically, the result is very, very nice. The result is very, very nice. If your point is inside the sphere, your electric field is going to be equal to 0. If your point is outside the sphere, it is going to look as though all of the charge is concentrated in the center. Okay, so this is a, I would say, somewhat important concept that you are going to have to use multiple times. Okay. The rest of the question on this page, I will let you guys do in your own time. It is not essential for you to finish all of them. Some of the integration can be quite cancelled, so I won't put too much stress on it. Okay, now we start to get to the more interesting things. Basically, okay, let me just get that. Okay, basically we are done with electrostatics. The entire electrostatics can be summed up with, okay, this is Coulomb's law. We're just applying Coulomb's law to a charge distribution. But the problem with applying Coulomb's law is that it is very, very annoying. It is very, very annoying in the sense that you have lots and lots of integrations for you to do, and you have it is just basically it is not a fun way to do electrostatics. And the rest of electrostatics is really just about developing how can I avoid doing integrations. Okay, It is about looking at the electric field produced by a point charge, and then going, what properties does this electric field have? Okay, what properties does this electric field have? And in general, we understand that the electric field is a vector field. So basically, it is at every point in space, right? It is given by a specific vector. If you guys know anything about vector calculus, is that normally vector fields like this have interesting features with their divergence and interesting features with their curl. And for those of you who have never ever heard the words divergence or curl before, don't be scared by what these terms are. Basically, the reason I'm here is to explain to you what the divergence is and what the curl is. And for this particular worksheet, we are only interested in the divergence. I'll cover curl and gradient in the next worksheet. Okay, so pay attention. This part is going to be rather important. So the first question is, what is divergence? And I'm not going to start off with giving you guys a definition, because honestly, if you look at the definition of divergence, you're not going to take much away from it. So when you have a vector field, you can think about what are the ways I can use, what are the ways I can describe this vector field? And one of the things that you can say, right, is, are the vectors moving away from a point or towards a point? In specifically, how fast are the vectors moving away or moving towards a point? And why this is an important question to ask is that if you think about what vector fields usually represent, things like velocity, the quantities of what is exiting and what is entering, these all have very physical meanings, which makes them interesting to look at now. And in particular, I'm not going to start off with an example of the electric field. I'm actually going to look at a much more intuitive thing, which is, let's just imagine you have a container with lots of fluid. Okay, so let's just say this is water. Oh my goodness. Okay, let's just say this is water. And what we're interested in, right, is that how does this water flow? In particular, right, let us take a random surface, and I want to ask the question, what is the mass exiting or leaving this surface? What is the mass exiting or leaving this surface? Okay, and let us take a look at it like this. Okay, so let's just imagine you have an arbitrary surface. If we were to focus on, let's just say, a tiny area of this surface, okay, and I'm going to just take this area out. If this area is small enough, right? What you're going to expect, right, is that the fluid at this particular point, right, is going to have uniform velocity. Is that clear? Because when you zoom in anything big enough, everything becomes uniform. And so if let's just say, okay, if let's just say this dA has some velocity v in this direction, okay, I should not be using a pencil. The pencil is not very clear, huh? Then in time dt, right, let's think about how much fluid has exited the system. Well, this length is going to be v dt, right? This length is going to be v dt. So the volume that has escaped is dA times v dt. Is this clear? This is the volume that has escaped. So volume escape. So what is the mass that has escaped? Well, it's just the density times this. So this is the mass that has escaped. Okay, so mass escape. Now, what happens if this dA, right, has velocity moving in a direction like this? If the velocity moves in a direction like this, right, we're going to expect it to form something like a parallel pipette, something like this. So this length over here is going to be v dt. And if I draw a side view, let's just say this angle is theta, right? This length over here is going to be v cos theta dt. Okay, so yeah, we're going to expect something like this. So the volume that has escaped from here, right, is going to be or the mass, let's just skip straight to the mass, is going to be rho dA v cosine theta dt. Is that clear? So far so good. Okay. So now I can move on. So in general, right, if you have a surface dA, so we're going to imagine this is a surface, but I'm going to draw it as a line. We can represent this surface as some vector that points perpendicular to it, okay? That points perpendicular to it. And the magnitude of this vector is just going to be the size of this plane, okay? The size of whatever shape that you have taken. And let's just say at this particular point in time, right, the fluid at this point is moving at some velocity v. So the amount of mass that escapes from this particular area, right, is going to be rho times v dotted into dA times dt. So this is the mass that escapes in time dt. Okay, so instantaneously, how much mass is escaping? Well, you just throw away the dt term. And if you were to talk about the entire surface, what you can do is that you can integrate this over everything. And basically, this is the mass that is escaping. Jesus Christ. Okay, I'll fix the camera problem for next time, but for now, just bear with me. So this is the mass escaping the entire surface. So you can imagine that whatever surface that you pick, right, this is going to be the mass that is escaping from it. And for a fluid, we're usually going to expect this to be zero, but there are situations, for instance, if you throw something hot inside, the fluid starts to expand, then this term may not necessarily be zero. But the thing that we're actually interested in, right, is what happens when this S becomes very, very small. Okay, what happens when this S becomes very, very small? And basically, what happens when the S becomes very, very small is that this thing becomes what we call the divergence. And in order to get an understanding of what this expression will look like when S is very, very small, let's just consider a cube. And this cube is at positions x, y, z. Okay, it extends, let's say this is dx, it extends, so this is the x direction, this is the z direction. So this point over here is going to be x plus dx, y, z. This point is going to be x, y plus dy, z. And this point is going to be x, y, z plus dz. Okay. Okay. The first thing that I'm going to do to make this a little bit simpler is that this rho v is very distracting. So I'm just going to call rho v as a single thing. I'm just going to call it, let's just call it b. And well, what is the flux that escapes this that escapes this system? Or basically, what is the mass that is coming out from this? What is the mass that is coming out from this tube? In order to figure out what this mass is, we're going to look at the faces one by one. And let us take a look at this face first, which I'm going to call surface 1. Okay. So we know that the expression we're looking for is going to be b dot dA, right? So what b dot dA does is that it takes the component of b in the y direction, okay, in the y direction, and it throws away the component of b in the x and the z direction. So the total thing that is going to enter in here, we're going to expect to be by minus dx dz. Okay, and the minus sign here again is because remember dA is pointing outwards. So dA looks like that. Now, if I were to take a look at this surface, right, S2, what is the mass escaping from this surface? It is going to be by as well, except this by is going to be evaluated at some additional y plus dy. And we're going to have dx dz. So far, so good. Again, so the flux or the mass exiting from this surface is going to look like by evaluated at x, y, z. And the mass exiting from here is going to be by evaluated at x, y plus dy, z. So the total contribution of these two, if you put them together, right, is just going to be by x, y plus dy, z minus by x, y, z times dx dz. Okay, and this should look very, very reminiscent of our partial derivative definition. So what you can do is you can just divide top and bottom by dy, and what we do get is that this is going to be equal to partial by partial y dx dy dz. And dx dy dz is really just the volume of this tiny thing. So this is going to be equal to dv. Okay? And what we can do, right, is that we can sum up the contribution of all 6 of these surfaces. And well, I'm not going to go through the derivation of the other 2 surfaces. It looks exactly the same. But what we do know, right, is that as s becomes very, very small, this thing is going to become an expression that looks like this. And this first part is what we term the divergence. Everyone still with me? If you guys want me to repeat anything, just let me know, because this is an important concept for you guys to understand. Okay, so this is the okay. Once again, remember when we're talking about this expression, right? What we really mean is this is the mass entering or exiting this dx by dy by dz block. And if you were to look at a bigger mass, right, a mass that is of non-trivial size, right, what you can do is that you can always just break this mess up into tiny dx plus dy plus dz blocks. Okay, and in doing so, right, for each of these tiny blocks, this is satisfied. So what you do know is that if I were to integrate this over the entire volume of the space, right, what I'm going to get is the total mass flowing out. In other words, I can always just equate these two together. Okay, so these two are always the same. And this is the divergence theorem. This is basically the divergence theorem. Okay, and this is a theorem that we're going to have to refer back to a lot of times. Let me just give you a demonstration of why this theorem is particularly useful. For instance, in fluid flow, right, we've already established at the beginning that given a certain surface, the amount of mass that exits is going to look like this. But the other way to write this mass, right, is to just integrate your density over the volume of the space. So in other words, these two are the same. So remember, this is the mass exiting per unit time. This is the change in mass of the entire thing per unit time. And what we can do is we can apply the divergence theorem to this side of the formula to get the and okay, we can bring this ddt in to get this. So and since this is true for every point in space, right? What we do know is that these two terms must be equivalent. Okay, so these two terms within the integral must be equivalent. And this is a very important equation in fluid dynamics. This is your mass continuity equation. It's just an example of why the divergence theorem is very, very important. Okay, so this has taken an extremely large tangent. I'll give you guys a small summary over here. So again, the definition of the divergence we define as this. And the reason why we define as this, don't forget, is because what we were interested in at first was how much is flowing out of a given surface. Okay, so for instance, if you were to look at a vector field that looks like this, right? This is something with positive divergence. A vector field like this has zero divergence, and a vector field like this has positive divergence. Okay. And the divergence theorem, which I have stated over here, right, is basically just saying that, okay, the forces within your volume, right, is going to be equal to the flow coming out of the surface. Yeah, so this is a short summary of the divergence. Okay, now, okay, back to Gauss' law. So once again, we are returning back to this very simple equation, because what we do know is that any charge distribution, right, has to be made up of a bunch of point charges. So before we talk about charge distributions, it is always good to first talk about a single point charge. And what we can do with this point charge, right, is that we can try and find its divergence. But before we try to find its divergence mathematically, right, we always go back to thinking of the fact that divergence is really talking about how much is flowing out of a surface. So in order for us to get an intuitive understanding, right, it is a good idea to just draw out this vector field. Okay. And one way we can yeah, that is an accurate interpretation as well. That is an accurate interpretation as well. But the problem with saying how much of the vectors is pointing towards it, right, is that it doesn't make sense to say something is pointing to a point. You always have to talk about a surface, you see. So it makes a little bit more intuitive sense to say how much is escaping from a surface or how much is entering a surface, rather than how much is pointing at a specific point. So the divergence is the limit where this surface becomes very, very small. So it is correct, the interpretation is correct. It's just that, I mean, there are always many ways to look at one thing. Okay. So back to the electric field. One way we can try and visualize this electric field is that, okay, we can just simply plot out all of the vectors. So the vectors going further and further away, they become shorter and shorter. So we can just, draw it out like this. But this is a very cluttered way of representing the E field. A better way of doing it, right, is that since these fields line up nicely, right, we can just, join all of them up together. And here's the interesting thing. When you join all of these E fields together, right, it looks as though we have lost information. Because at the beginning, right, we were saying, the length of this vector represents how strong the E field is. But when you join it together, the length disappears. So basically, the information of the strength of the E field has disappeared. But the interesting thing is that, okay, E field falls off at a 1 over r squared rate. And surface area also falls off at a 1 over r squared rate. So if I were to just draw out a fixed number of points, right, like a fixed number of lines, right, if I draw out n lines, I'm going to expect, right, the number of lines per unit area to be a representation of the strength of the electric field, because they fall off away from the origin at the same rate. Is that clear? And because of this particular idea, right, what we can do is that we can define a term where we call flux. And basically, flux is just, you can just think of it as E times A. Because we've established the fact that your number of field lines per unit area is going to be proportional to the field strength. So this is just going to be a term that tells you, how many field lines there are in this given area. And the okay, and this particular thing, right, is simply just going to be hang on. Yeah. So this term, right, this phi of E, right, this flux term is just going to be proportional, right, to the number of electric fields going through a specific area. And I say this very loosely because, of course, we know that there are infinitely many electric fields passing through any given area. But the thing is that if I were to say take a sample of, let's just say, I only want to draw 5,000 electric fields, then this thing is going to be roughly proportional to, okay, how many electric fields are going to pass through this specific area. So here is where the crux of the problem comes in. So if we were to consider a closed surface, right? A closed surface. If your point charge is outside of this surface, right? If your point charge is outside of this surface, an electric field that comes into the surface, right? Okay, of course, it doesn't really look like the squiggly line, must also exit the surface. So this thing contributes nothing to your flux. This has no contribution, no contribution. This has no contribution to flux. On the other hand, if you were to have a charge that is inside the surface, all of its electric field lines are going to pass through this surface. And the more interesting thing, right, is that it doesn't matter what surface you take. I can take a surface that is bigger and scarier, and the same number of field lines are going to pass through both the outer surface and the inner surface because it encapsulates this point charge. So what this really means, right, is that the flux going through this surface, right, is a representation of how much charge is inside. Because if the charge is outside, it has no contribution. If the charge is inside, this contribution is the same no matter what. And this is in essence what Gauss law is talking about. Okay, so Gauss law is just a mathematical formulation of this idea. And if you want, you can do the integration of the flux through a surface, and you can find out that, okay, it is indeed an invariant law. But this is really just, it's beside the point. This doesn't really add anything to the intuitive understanding. It is just giving you okay, this is the absolute mathematical description. Always just keep in mind that when you have a point charge, the flux that it produces, right, or the flux at a distance passing through an area is a representation of how strong the electric field is. And this is why this statement is true. Okay. And yeah, for a single point charge, this again, this is the same. We can just apply the divergence theorem directly to this, and then we get this is the differential form of Gauss law. This is the integral form of Gauss law. So this is the form that is more applicable to Olympiad questions because usually we only use Gauss law when there are nice symmetries to abuse. Okay. In fact, when there are not nice symmetries to abuse, Gauss law is more tedious than anything. Because it tells you what is going on the surface of something that is that has size, and we're not interested in what is going on over the entire surface. We're interested in a specific point, which is why typically Gauss law in integral form is only useful if we don't, let's just say, E is pointing in the same direction everywhere, or E has the same magnitude everywhere. In general, when you're solving electrostatics problem, it is much more useful to use to solve your Poisson's equation and to solve your Laplace equation, which are going to be topics for future worksheets. Okay. So far, any questions on Gauss law? Any questions on what the divergence means? Okay. And let us actually just take a look at an application of Gauss laws. And I'm going to do the exact same problem. Okay. So why the charge outside doesn't contribute? Basically, if you have a charge outside of the surface, right? If you have a charge outside of the surface, whatever electric fields that it produces, right, must pass in one side of the surface and it must come out. Because you can't have an electric field just okay, you can now. If there is a negative charge here, you can have an electric field that terminates, can you? You can, huh? Oh, okay, fine, yeah. So let us just not talk about what happens if you have a negative charge there, because you can just apply the superposition principle and say, yeah, the answer is going to be the same. But if you have a point charge outside of a surface, right, it will pass through and it must exit. Okay, it will pass through and it must exit. And because it passes through and it exits, right, the flux contribution over here is going to be cancelled out by the flux contribution here. So in general, this is going to have no contribution to the flux. Does that make it clear? Okay, can. So now we are going to use Gauss' law to answer the question. A spherical shell has constant surface charge sigma. What is the electric field inside? What is the electric field outside? And the good thing about this system, right, is that we know that it is spherically symmetric. Since it is spherically symmetric, what we do know is that at any point here, right, the electric field is going to be pointing radially away from the center, and every point on the same radius, right, is going to have the same magnitude. Okay, every point on the same radius is going to have the same magnitude. So what is the flux going through a sphere of radius? Let's just say, I'm just going to call this, yeah, I'm going to call this Z lah. So the radius of this is Z. Well, we know that E is going to be equal here, and we know that it is already perpendicular to the surface. So this is just going to be equal to 4 pi Z square times E, right? Okay, so I know the electric field is a vector, but in this particular case, since we already know the direction, we can just write it as a scalar quantity. And this is going to be equal to 1 over epsilon 0 times Q that is enclosed inside. So the Q enclosed inside is going to be sigma times, I'm just going to write Q. Okay, I'm just going to write Q. So if you just do the division, E is just going to be equal to 1 over 4 pi epsilon 0 Q over Z squared. See, super easy. On the other hand, if you were to look at a sphere that is on the inside, right? Well, we know that this Q enclosed, right? This Q enclosed contains nothing. So there is no charge enclosed within this sphere. So the flux through this sphere must be 0. Okay. And if the flux through this sphere must be 0, and there is radial symmetry, we know that the electric field in here must be 0. So really, this is just a two-step argument as compared to the ridiculous integration that you had to do previously. But again, keep in mind that Gauss' law is really only useful if you have symmetries to abuse. Okay, if you don't have a symmetry to abuse, like for instance, let's just say I have this random charge distribution, and I were to take a surface here, right? Okay, we know that if you do E dot A and you integrate over this surface, you're going to be getting 0. But the problem is that your E points in all sorts of strange directions. Your E point doesn't point in a nice direction. So this really gives you no information about what E is at this specific point. It doesn't give you information about what E is at this specific point. So again, Gauss' law is only useful if you have symmetries to abuse. Can it be adapted for gravitation? That is a good question. The only thing that is different, right, is the proportionality constant. Because your Coulomb's law and your Newton's law of attraction, right, it is the same thing. There is a constant times something over r squared relation. So yes, this can be adapted perfectly to gravitation. It is basically the same thing. Okay. There are actually a couple of very interesting questions in this worksheet. And in particular, what I want to go through is, actually, I really want to go through all of these questions. Let's see. Okay, let's do some of the easier questions here. 1.4.3. Then for the slightly more difficult questions, I'll give you guys time off and we'll go through in the next lesson. How does that sound? Okay, so 1.4.3. Okay, for those of you who are new to vector calculus, who are new to all of these strange integrating over a surface ideas, right? This topic is going to seem a little bit difficult at first, but once you start doing the problems, I trust me, it does get easier. Okay, so 1.4.3 is an easy question. I'm going to give you guys 4 minutes to think about it, and if you are done, just WhatsApp me your answer. Q over 24E is right. Okay, I'm going to give the rest of you guys time to think over the answer, but you who have WhatsApp me, prepare to present your solution. Huh? Okay. If you want, you can draw a diagram and take a picture of it, send it to me lah. If it helps make the explanation clearer. Okay. And once you're done, you guys can try problems 1.4.4b. Yeah. So let me just type out the questions I want to use. So, okay, so I'm planning on going to show you these two questions. What's A? Oh, A is just a constant. Yeah. Or maybe I should resonate the question, huh? Hi. Okay. Okay. Yeah. So unmute yourself. Just go through your answer.
Okay, so basically this cube, the charge sitting at the corner of the cube, you can think of it as a charge sitting at the center of a larger cube, and then you can see that the flux through every single side of this larger cube is the same. So we take the total flux, which is Q divided by epsilon 0, then we divide it by 6, since there are 6 sides. And then we realize that the electric field lines that pass through, they only pass through 1/4 of one side. So it's Q divided by 6, then divided by 4, then divided by epsilon 0.
Yeah, so that is absolutely correct. I have nothing to say about your answer except for it is correct. So good job. If you guys want a, actually my written answer is also not very well. Yeah, it's also not very well explained. So yeah, basically what you said is correct. Okay, now 1.4.4.b. Okay, this question is a little bit tricky. So I'll give you guys 5 minutes to do it. The math is not tricky. The tricky part is explaining the math. So once again, if you're done, WhatsApp me your answer. Okay, so charge density, or when you see rho, right, remember rho is always talking about charge per unit volume. Okay, rho is always talking about charge per unit volume. And the answer that you get is supposed to surprise you. Oh, but by the way, it's not A over 3. It's there is no over 3. Yeah. It is A. Yep, that is correct. Okay, you who have done the problem, want to unmute your mic? For the rest of you have taken a look at the problem already, right? Anyone else got the answer A?
I'm not really sure if this is rigorous, but
Okay, so your answer is A, right?
yeah.
Okay, it's actually epsilon, not A. But that's beside the point. Walk us through what you did.
Oh yeah, sorry, I forgot that. But basically, because EA equals to because EA equals Q over epsilon 0, then so basically Q. So basically, Q. So you have the E here. So that means the other side. That means that is Q over epsilon 0 times the over AX. Wait, sorry.
Do you perhaps want to write something down and send it to me?
Yeah, I forgot to do the math. Oh, sorry. So the other side is so charge over area equals to AXX hat.
Okay. Maybe I should have made this question clear. The A in this question is not area. The A is just a regular constant. So if you guys want to write it down, make an amendment. A here is a material constant. Not material constant. It's just an arbitrary constant.
Yeah. Okay. Sorry. So I'll just restart. So basically I just converted E into I forgot the 1 over epsilon 0, but 1 over epsilon 0 times charge over area using Gauss's law, and after that, so 1 over epsilon 0 times charge over area equals to AX x hat. So if I volume, so charge over volume would just be Q over AX. So I divide both sides by x and multiply by epsilon 0. So rho would be epsilon 0 times A.
Okay, the argument is a little bit difficult to follow, but you took a cubic Gaussian surface, is it?
Sorry, what?
Like maybe you want to actually write down the math because I'm struggling a little bit to follow the argument. Yeah, snap a picture and send it over to me.
Okay.
Okay, E equals to 1 over epsilon naught Q over A. This A here, the area you're talking about what area?
Sorry, can you repeat the question?
Okay, your E is 1 over epsilon 0 Q over A. This is correct. But this A here refers to what area? What area have you done applied your Gauss law?
Along the YZ plane.
So it is a cube, is it?
Sorry, what?
You see, you can't just apply Gauss law on a surface. You have to apply it on a volume that is encapsulated within a surface. So it doesn't make sense to say okay. It doesn't make sense to say, right, that okay, E dot dA integrated is equal to rho over epsilon naught, because a surface by itself cannot have any enclosed charge. In order for you to have an enclosed charge, you need to have some volume. So you can talk about a Gaussian surface of a cube, of a cuboid, of a sphere, but you cannot talk about a Gaussian surface of a plane. It needs to have some volume in which it contains charge. Are you following me?
Yeah.
So it's just the way that it's presented. I mean, you have some hints of you know what is going on, but the way it is presented makes me think that it's not quite correct, even though the answer is correct.
Okay.
Anybody else manage to get A? Nobody else? Okay, that can't be true. The question isn't difficult. Okay, I'm going to pick a random person on this list, right? 15 of 25 in call. Okay, okay. How should I pick? +6, +6. Okay, let's just go with the first person on the list. Benny, did you manage to solve the problem? Are you still with us? No. Okay. Does not computing. Manage to solve the problem? Did not compute? Okay. So this question is very simple. It is actually just asking you to apply Gauss law in differential form. Okay. It looks like this: Ex yz is equal to Ax xz. So what does Gauss law in differential form say? It says that the divergence of E is equal to rho over epsilon naught, right? Is equal to rho over epsilon naught. So what you can do is you can simply take the divergence of this. So what is the divergence of this? Well, we have partial x, Ex, plus partial y, Ey, plus partial z, Ez. Now there's no Ey term, there's no Ez term. So partial x, Ex is just going to give you A. So we have A is equal to rho over epsilon naught. So rho is equal to epsilon naught A. Okay. Now, does this answer surprise you? And the correct answer is supposed to be yes. You see, rho equals to epsilon naught A. This means that the volume charge everywhere is a constant. Okay. So you can imagine this system, it's everywhere has the same charge per unit volume. Yeah, the electric field points in the x direction. Oh, no, you're supposed to be surprised by this question. It is a surprising question. So there is a correct answer. Okay. So let me explain why this answer is surprising. This thing has a constant charge per unit volume everywhere. It has the same charge per unit volume everywhere, yet its electric field has a direction in the x. It points only in the x direction. So how can this symmetric system produce an asymmetric electric field? That is the crux of the question, and that is the thing that I want to pose to you guys now. So give a moment and think about why. And if you have an answer, you can just WhatsApp me. I'll give you guys 3 or 4 minutes to think.
Okay, what's the question?
Okay, the question, let me repeat. If you apply Gauss' law to this particular problem, you end up that the volume charge is going to be equal everywhere in space. You're going to expect an equal volume charge of epsilon naught A everywhere. And if the volume charge is the same everywhere, right, this system, right, is symmetric everywhere. Yet the electric field it produces is asymmetric. So why is this so? I see we have lost some people. Okay, never mind. Anyone have an answer? Okay, I'm just going to answer myself. The reason for this, right? Is that this electric field is not a physical electric field. When you are applying Gauss law, right, in differential form, you have to keep in mind what you're doing is you're taking a derivative. And whenever you're taking a derivative, right, you will lose information. So for instance, let me ask you a question. Okay, if I tell you that the gradient of this graph is 3, can you tell me what the graph is? Well, obviously not, right? There could be a multitude of different graphs with gradient 3. But if I was to tell you, okay, the gradient of the graph is 3 and it passes through the origin. Now, okay, we know perfectly that this is the graph y is equal to 3x. So the same thing is at play here. When you apply Gauss' law, right, you're doing differentiation, so you are losing some information. So how can you know whether or not your answer is correct? It's because you're actually imposing a very specific boundary condition that you don't realize that you're imposing, which is that E is expected to go to 0 as your distance goes to infinity. Okay, so in fact, right, as long as, okay, let's just say I have an arbitrary field, and this arbitrary field has a divergence of 0, right? If E satisfies this equation, then so does E plus F. Okay, so does E plus F. So what this means, right, that this thing, right, doesn't have such a nice boundary condition because it doesn't fall off to 0 when your distance goes to infinity. It keeps on increasing and increasing and increasing. And this is something that not a physical system can do. And so when you take the derivative, you get, okay, so this is the answer. And this is indeed one possible solution. It's just that this particular solution carries no physical meaning. Okay, and this is something that needs to be made clear because you can apply Gauss' law to the same situation and you can end up with different results. For instance, right, if you have a parallel plate capacitor, right, you're going to expect the electric field inside to look like this. No, F here is an arbitrary field. F here is not force. F is just F for field. Okay, so let's just say you have a parallel plate capacitor and you have a point charge with electric fields that look like this, right? If I were to take a Gaussian surface over here of the exact same size and exact same volume, right? Well, these two satisfy the same equation. They don't encompass any charge. So you're going to expect the divergence of E here to, okay, not talking about Gaussian surface here, but you're going to expect the divergence of E here to be equal to 0. Yet they give you two very distinct fields. Okay, And the reason for this is to keep in mind that you are always differentiating when you're applying the Gauss law in its differential formula. And so when you want to get back your or rather the answer that you get, right? So basically what I'm trying to say is you can go one way, but you cannot go the other. And the analogy to put again is that let's just take a look at what happens if you have a graph. I can say, oh, the graph has a fixed gradient, but I cannot say, given the gradient, find the graph. I have to give you something else. And the same is true. With an E field, I can always find a row, but I cannot say, given a row, find the E field, unless I also state, okay, E field falls off to 0 as R goes to infinity. Okay? Everyone follow the logic? Okay, I think we've gone through a lot of things this week. And next week our lesson will be on Wednesday. and we'll take things a little bit more tame. So basically next week we'll just be going through the questions in this worksheet lah. So we'll be going through the math, just making sure you guys can handle the integrations that come up to you during the test. Yeah. And before I end of this week, I actually have a test question. I have a test question that is going to not be answered today. Basically, I'm giving you guys 1 week to solve this problem, okay? I'm giving you guys 1 week to solve this problem, and anytime during the week, you can just WhatsApp me the problem, WhatsApp me your solution. And this will be the first thing that I'll go through next Wednesday's lesson. So pay attention. The question is very simple. It can be explained in 2 lines. I will not tell you if you're right or wrong until next week. So just WhatsApp me your solution and enjoy the silence. Okay, everyone, let me just send it in. Okay, and the thing to take note about this question is be very careful about how you explain your answer. Okay, the math itself is not difficult, but the explanation itself takes up the bulk of the interestingness of the question. Okay, fine. I'll tell you if you're wrong lah. Okay, so for the remaining 12 of you who soldiered on with me all the way until 10 o'clock, are there any questions? Okay, if there are no questions, then I'll just give you guys a recommended book. This is the recommended book. So for those of you who are interested in going to engineering, right? This is one of the better books on electronics that you can get. It is also very, very thick. Okay. Yeah. If you guys want to take note, go here lah. And if nothing else, then I'll just end the lesson here lah. So have a nice time. Do my test question and see you next Wednesday.